Okay. Oof. There we go. Yeah. That's better. Okie dokie. So we're continuing chapter 5. Talking about gases. And last class we were talking about the ideal gas law. Perv nerd. Right? I think hopefully everybody's relatively familiar with this guy. There are going to be plenty of problems in the homework just dealing with the ideal gas law. A couple of the new topics that we talked about were effusion and root, mean, square, velocity. Right? So if you have questions about those topics, definitely let me know. But I'm not going to go too much more into those. So what we have left is talking about today Dalton's law of partial pressures. Oh my God. Partial? There it is. Which you guys see in Chem 152, am I correct?
Yeah.
Sorry, what was the question?
Dalton's law of partial pressures. You guys have seen that before?
Yeah.
Okay, that's what I thought. I'm pretty sure you cover that in Chem 152, but we'll go through it just in case you don't recognize it. And then the last thing we want to talk about is non-ideal gas behavior. So last class we kind of talked about what it means for a gas to behave ideally and when we are able to use this ideal gas law, right? So we're going to talk a little bit about how that behavior breaks down. And we're going to go through one of the equations that deals with that. There's probably 5 or 6 different equations that make different approximations for non-ideal behavior. But we are just going to look at the one called van der Waals equation. Okay. Beep boop beep boop. What else did I want to say? Okay, so that's what we're gonna do today, and then I wanted to go through and do some problems from the chapter 5 homework, just to make sure you guys know, because there's a pretty steep difference in the types of problems that we're going to be handling with PV equals nRT in Chem 200 versus Chem 152, especially when it comes to gas stoichiometry problems. So I just want to make sure you guys have at least seen a couple of those and know some of the things you want to look out for. Okay, so first things first, Dalton's law of partial pressures. Partial. Oh my gosh, there it is. Dalton's law of partial pressures. So Dalton's law of partial pressures says that the total pressure, or the ambient or atmospheric, right? The total pressure, the one that can be measured barometrically, is going to be equal to the sum of the partial pressures of the gases in a mixture. right? So a lot of the times when we're talking about our ideal gas law, we're kind of assuming that we're just working with one gas or that our system only involves one gas. But when we're working with multiple gases in a mixture, that's when Dalton's law of partial pressures comes in. And this is actually much more common than working with an isolated gas, right? So if you think about the most common gas you guys have experience with, what is it?
Propane.
Okay. Oh, I was going to go for air. Yeah, for sure. Right? Air is a mixture of oxygen, nitrogen, and then some other trace gases, right? But generally speaking, it's really hard to not have gases mix, right? So gases mix spontaneously, right? And the reason or the force that drives this spontaneous mixing is called entropy. Okay? So entropy is the drive to spread out energetic burdens. Did we talk about entropy earlier in the semester?
I don't think so.
I don't think so either, but
No.
Okay, cool. So a lot of people like to give the definition of entropy that says that it's basically chaos or dispersion. Those are not bad definitions, but I like to think about entropy as being a way to spread out energy. So if you think about energy as being the cost of nature, right? Then this would be the equivalent of nature's tax, right? So instead of having the energetic cost fall on a small number, right? A small number of things, we want the energetic cost to be spread out as much as possible over as many things as possible, right? By doing this, we're able to spread out the energy and minimize the energetic cost to all of the things that are sharing it, right? So one of the consequences of this is gas mixing, right? Another one is dispersion of gases, right? So we know when you put gases, if I were to take all of the air that's in this room that I'm in right now and put it into one little corner and then let it go, what's going to happen to the gas?
It's gonna spread.
It's going to spread out, right? It's going to disperse through the entire room, okay? So that's, that process of dispersion is entropically driven, okay? So when we get into Dalton's law, P tot is going to be equal to, let's say we have a mixture of let's say we have a mixture of two gases, right? Let's pretend like we're talking about air because that makes it easy. So air is about 79% nitrogen approximately and about 21% oxygen. That's kind of a fib, mostly about 19%, and then other trace gases. So if we know that we have these percentages of the of each gas here, then we know that these percentages need to add up to be the total, right? The same kind of concept is happening here with the pressures. So what we're saying is what's the standard pressure?
Per area?
The standard pressure as in STP.
1 ATM, right?
Yeah, so we have 1 atmosphere, right, would be our generalizable total pressure, right? So of that total pressure, what part of the pressure would be due to nitrogen?
Would you just take, so it'd be 0.791, right? Out of 1.
So all you have to do is take the total atmospheric pressure, right, and multiply it by the percentage as a fraction, right? Does that make sense? So the pressure, partial pressure of nitrogen in this case would be that, right? So then what would the partial pressure of oxygen be?
0.21.
Exactly. Does that kind of make sense, guys? Pretty easy, right? Hopefully, mostly.
It is, yeah.
Yes. Yeah.
Cool. So there's a formal way of defining these partial pressures, but I think they're relatively intuitive. But the partial pressure of a gas is equal to the pressure of the total times this guy chi, which is the mole fraction, right? So the mole fraction is literally just moles of whichever gas we're talking about divided by, oops, sorry.
Wait, what's that?
This is chi. Chi. It's a Greek letter.
Oh, okay.
It's a squiggly X.
Okay.
Sorry,
What's that stand for?
Huh?
What does that stand for?
Chi is the mole fraction.
Mole fraction.
Yeah. And so what we're saying is for a particular gas, the mole fraction will be the number of moles of that gas divided by the number of moles total, right? I think you guys see this in solutions again too, so this is going to come back. But there's multiple ways to get to the partial pressure. This is probably an easier example. This would be the more complicated way that you might see it. But does it make sense that the mole fraction and the decimal of the percentage is the same thing, basically?
Yeah.
You guys with me on that? Cool. Questions about partial pressures? So these become really important when you're talking about gas reactions, right? Or gas stoichiometry, which is what we're going to talk about a little bit later. Questions? Awesome. Okay. So the last thing we want to talk about is non-ideal gas behavior. So we have our ideal gas law. Whoops. PV equals nRT, right? And we said that one of the ways that ideal conditions can break down is if we have strong intermolecular forces. Which is a really fancy and complicated way of saying particles attracted to each other. Oof. Right? So you guys remember we were talking about the postulates? We said that one of the excuse me. One of the postulates assumes that the attraction between particles in a gas is negligible, right? And if this wasn't the case, what would happen to gases? If the attractive forces between gas particles were really strong, what would happen?
It would condense into liquids or solids.
Exactly, they would condense, right? But we know that not all gas particles are going to have the same particle attractions, right? So the stronger your intermolecular forces are, or the particle attractions, the more this behavior is going to change from ideal behavior. So we have a term that's added to PV equals nRT to account for particle attraction. You guys feel like my handwriting is getting worse? I feel like it's getting worse. No? Maybe it's harder because there's lines on this paper. You guys know how I feel about lined paper? Have we had this conversation?
No, we haven't.
I hate it. I hate it so much. I started when I went to UCSD. I started buying those like art sketch pads, and I would just use those, and it was so much easier. I don't know why, but lines really bum me out. Like too
I
confining.
just can't write a straight line without it, but I don't like the limitation or how it just like gets in the way of my font.
Right? Doesn't it feel like intrusive? I don't know. Just wait, when you guys take organic, you're gonna understand what I'm talking about. You're like, these lines, get them out of here. This is being recorded. I should watch my mouth. Okay. Anyways, so when we're looking at this factor, it alters the pressure, right? So we have our pressure term up here. We're going to add a corrective term that has this little guy A is an, excuse me, sorry, my brain is very dumb right now, is a correction term based on whatever gas you're talking about.
Hey, Professor.
Yeah.
Is that square to the power of the 2, is that applied to the whole?
No, that's just to this guy, and I haven't filled in the rest of the equation yet, but I'll get there. Okay. So this value is not something that you have to memorize or know. This is something you would look up in a table. Right? These factors are exactly what you think they are. This is the number of moles, and this is the volume, right? Now, what is this quantity basically? This N divided by V. What did we say it was last time?
Mole fraction?
Not the mole fraction.
Moles by velocity?
Not velocity. That's volume, right? It is kind of a molarity, Jerica, but when we talk about gases, we kind of call it the gas density or the gas concentration, right? So remember when we were talking about the postulates and we said there's certain things that can happen to break down, right? So the factor that that corresponds to this correction for intermolecular forces is modulated by the square of the gas density. Does that make sense, guys? So basically, this correction term to the pressure is saying that the pressure in a gas is going to increase as the density in the gas increases, proportional to this factor that accounts for the attraction between those particular gas particles. Does that make sense, guys? Kind of, sort of?
Yeah.
Questions? So that's one of the correction terms, right? That we're just sticking into our original PV equals nRT equation, right? You guys still with me?
Yeah.
Cool. Questions? So what I really want you to know about, excuse me, about the non-ideal behavior is that we have these kind of ad hoc terms that we add in to correct for certain behaviors, and I want you to know what they represent, right? So in this case, the A term is correcting for intermolecular attractions, right? Interparticle attractions. Coolsies? Uh-oh. Can you guys still see me?
Yeah.
Yep.
Okay, it's telling me my internet connection is unstable, so we'll see what happens with that. All right, so the second correction term, we had our P and V squared. The next correction term is to the volume, right? So this one has a little letter B and the number of moles multiplied by it. And this whole thing is equal to nRT. So this second correction term, B again, is a correction term for whatever gas you're working with. And this term corrects for the particle volume. So if you guys will recall, we said that the one of the postulates of the kinetic molecular theory of gases is that we consider particle volume to essentially be negligible, right? So in a lot of cases, that's probably true, right? The particle volume is negligible. But there are some bigger molecules that are gases, right? And in these cases, particle volume may no longer be negligible. Does that make sense? Yes, Danica. Kind of.
Mm-hmm.
Yeah.
In the volume of just a single particle.
Right. So what we have here is a correction term, B, right? Which is modulated by particle size, right? Again, this is something you'd look up in a table.
Mm-hmm.
And the bigger this value is, the bigger the particle size, right? Everybody still with me?
Yeah.
Cool. So that B value is multiplied by the number of moles of gas in your sample, right? So this kind of makes sense. So we have a correction term for the size of the particles, and that is multiplied by or modulated by how many particles are in your sample, right? And what this term does is it reduces the overall volume of the container, essentially, right? It's accounting for the particle size here, subtracting it out of the total volume. Does that make sense, guys? Cool. So this is van der Waals equation. Everybody all right with me on that?
Was the one that we had before this also van der Waals equation?
No, that was working towards. So we were building van der Waals equation, right? This is the overall equation, right? So we talked about how to add in each of these correction terms, right? Both of them together give you van der Waals equations, or van der Waals equation, singular. Does that make sense, Kevin?
Yeah, I was confused because you said you weren't done with the other one, and then you went on to the next page, and I was...
Yeah, because, I mean, I have to, because the pages go away, right? Normally, if I was doing this in a classroom, I would have, like, built it all in one little area. But I can't do that here, so yeah.
Got you.
Any other questions about those? So this isn't going to be a huge focus. Mostly if you guys go on in chemistry, you'll deal with non-ideal gas behavior and non-ideal behavior in general in physical chemistry. So
Do we need to have the postulates memorized for the exam?
Memorized is probably overdoing it. You need to understand how and when they would break down, like under what conditions. Does that make sense? Also, you
a general understanding of what they are.
Yes, absolutely. Yes.
Okay.
Yeah. Yeah, I kind of assume that you guys have notes when you're taking these exams, but I think understanding is one of the things that I can most easily test you on that shows me that you're not cheating. You know what I mean?
Yes.
Cool. Questions about that? All right. Should we do some problems?
Sure.
Let's do it. Okay. So... Let's start with, maybe I have room here. Number 3 from the Chapter 5 homework has a weather balloon is filled with helium. To a volume of 1.61 liters at 734 torr. Right? What is the volume of the balloon? When the pressure drops to 0.844 atmospheres. And the problem says to assume that temperature remains constant. So anytime we're starting off with a problem like this, we just start off with our perv nerd, right? So I have an initial volume that's given as 1.61 liters, right? And I have an initial pressure that's given as 734 torr. Do you guys remember how to convert between torr and atmospheres?
Yeah. 760 torr is 1 atmosphere.
So 1 ATM is equal to 760 torr, or millimeters of mercury, right? These guys are the same. So I'm just going to go ahead and do that so that I can convert that guy to ATM right now. And then I want to find the final volume, and I have the final pressure is this. Oops, P2, excuse me. Oop. So, I have the pressure and the volume are the only things that are changing in this problem. Do you guys see that? It tells us explicitly that the temperature is not changing, right? We know that R is a constant. Will the number of moles of gas change?
No.
Almost never, right? The general way that we're doing problems with gases, we're almost always working in a container, and that container is usually sealed, right? So if the container is sealed, the number of moles is not going to change. So it's very rare to have a system where the number of moles will change. So if we know that only P and V are changing and that these guys are constant, oops,
then you can do a double convert.
Then we can do P1 V1 is equal to P2 V2. Now, technically, you could have memorized this relationship, right? This is, I always forget which one is which. This is Boyle's law, right? But I personally think it's easier just to remember perv nerd, and then you can derive all of these other relationships. So now all I have to do is solve for V2 and plug in my values, right? So what do you guys get for V2 when you do that?
You said what we get for V2?
Mm-hmm.
I got 1.84 liters.
You guys all right with that?
Yep.
Cool. So does it make sense that as the pressure decreases, the volume increases? So anytime you have two variables that are on the same side of an equation, as one goes down, the other one must go up, right? And vice versa. If they're on opposite sides of the equal sign, then they're going to change together, right? So these guys will be inversely related. These guys relative to the other side would be directly related. Does that make sense, guys?
Yeah.
Easy peasy?
Yep.
Cool. Any questions about that problem? So that's one of the like Chem 152 style problems, so that's on the easier side. Hopefully you guys feel that way. So let's look at, all right, so let's look at a little more complicated problem. So let's look at number 6. Let's see, cool. So this has a student, this one's a long one, wants to determine the percent of zinc in a zinc coated copper alloy. You guys know what an alloy is?
I forgot.
An alloy is just a mixture of metals. It's basically a solid solution. Okay, we'll get more into that in chapter 11. Excuse me. Beep, boop, boop. The sample weighs 3.9864 grams. After reacting with hydrochloric acid, the volume, whoops, of gas produced was 0.745 liters. The gas was collected over water. I'll talk about what that means in just a second. The partial, oh my gosh, pressure. I don't know why the word partial is so difficult for me, you guys. Partial pressure of water at 26.2 degrees Celsius is 25.509 millimeters of mercury. The ambient pressure is 783.28 millimeters of mercury. What percentage of the alloy was zinc? Oh boy. That's a lot, right? You guys do any problems like this in Chem 152?
Nope.
Nope.
Cool. Yeah, I found it.
Nope.
I think this one is infinitely more exciting. So hopefully I can convey my enthusiasm to you guys. Okay, so let's talk a little bit about the experimental setup that's going on here, right? So I have a piece of zinc copper alloy, right? And I've got a reaction flask. That's my beautiful reaction flask. Where I'm going to put the alloy in some hydrochloric acid, HCl, right? This reaction flask is hooked up to a hose, which is hooked up to a bottle, which is filled with water. This bottle of water is hooked up to another container that's empty. Whoa, empty. Okay? Beautiful drawing aside, I apologize, but what's happening here in the reaction is we're producing a gas, right? The gas is being forced into this container that's full of water, right? The water is being displaced by the gas, and the water is flowing into this empty container. Does that make sense, guys? Everybody with me?
No.
So, you can't just collect the gas in an empty container, right? Why not? Is an empty container ever actually empty?
Okay, yeah, I see your point.
Right? So if we want to know how much gas was formed in a reaction, we can't just collect a gas in a so-called empty container, right? Because it's not actually empty. So the way that we can collect the gas and know for sure that all we're collecting is that gas is by doing this method of water displacement, right? So if we have this container filled to the tippy top with water, right? Then we know that whatever gas goes in here and displaces the water, right? The gas that goes in here is only the gas that we formed in the reaction. Does that make sense?
Yeah.
Yeah.
Cool. Questions about that setup? Does this kind of, I think it's hard to understand what this problem is saying without understanding what it would physically look like in a lab. This is a super fun experiment, by the way. I'm sad that we don't get
As
to do
soon
it.
as I found out that the water was filled all the way to the top, then I was like, oh, okay.
Right. So basically what you're doing is you're saying there's no air in here, right? So it's completely to the tippy top with water. And so as the reaction proceeds, the water is pushed out into this other container and the gas is left over, right? So when we collect a gas over water, right? That's what they're talking about. Is we want to collect a gas, we want to know that the gas that we're collecting is only that gas, then we do it by water displacement. So the gas is collected over water. Does that make sense, guys? Cool. So we know that if a gas is collected over water, right, then at room temperature, some amount of that water is going to be vapor, right? Does that make sense, guys?
Yeah.
The amount of water vapor in a sample is temperature dependent, right? So the higher the temperature, the higher the partial pressure of water would be in here. Does that make sense? Cool. So anytime you see that a gas is being collected over water, and this is, again, one of the most common ways that you see gases collected for the reasons that we just talked about, it's automatically should be triggering you to think that you're going to need Dalton's law. Does it make sense why, guys? Cool.
Yes.
So,
Yeah.
Now let's talk about some solving. So before we get started on the meat and potatoes of the actual problem here, what do we need to do?
Write a reaction.
Yes. Yes, yes, yes. So we have zinc solid is being reacted with hydrochloric acid. And what are my products going to be?
Zinc chloride and hydrogen gas.
Yes. And remember, hydrogen is diatomic. So, what do we got to do to balance this bad mamma jamma?
Put
Put 2 in front of an HCl.
Exactly. Boop. Easy peasy. Now, before we go on, why is copper not reacting with hydrochloric acid? So we said we have a zinc copper alloy, right? So why does zinc react with HCl and copper doesn't? The answer starts with an A. What kind of reaction is this?
Single replacement.
Single replacement, exactly, right? What makes one single replacement reaction go and another one not? Somebody's got it. I know they do. Somewhere in your brain.
It's not affinity, is it? I don't know.
Cool. The activity series.
I don't know what that is.
Are you serious?
How how it like rates the elements.
Yeah, so it takes all of the metals. Go ahead, Teddy.
Of how strong they are.
How reactive they are.
In a single.
Yeah, exactly. So, especially for those of you who are going on to Chem 201, the activity series becomes really important when you're talking about making batteries, okay? So definitely check that out. I have some activity series worksheets that I'll post for you guys. You don't have to do them, but it's worth knowing about, at least for next semester. So basically, the activity series is just a ranking of the reactivity of certain metals and certain nonmetals relative to each other, right? So in this case, we're talking about zinc and hydrogen ions, right? And zinc is more reactive than the hydrogen ion, so it can replace hydrogen in this reaction. Copper is lower than the hydrogen ion, so it's not more reactive, which means that it cannot replace this. So that's why we can use hydrochloric acid to selectively react the zinc and not the copper. Does that make sense, guys? I feel like you guys want to punch me now. No, we're good? Cool beans? Easy? Did you guys not learn about the activity series at all in Chem 152? Really?
Never heard of it, honestly.
I did.
I never heard of it.
Okay.
Chem either, I don't think.
Okay, all right. That's not great.
I did.
Okay. All right, cool, Teddy. Brush through it. Okay. Yeah, I mean, it's not something that you have to like know. It's always something that you'd be able to look up. So if you needed to and you were trying to do a reaction, you could always look up the activity series. But knowing why certain metals will react with certain other metals and then others won't is the activity series, right? So you'll need to know that eventually. Okay, so we've got our balanced chemical equation, right? Now, I think it's really important at this point to outline exactly what we're trying to do in this problem, right? So we have the mass of the alloy, right, way up here. And we're looking for the mass of zinc specifically, right? You guys with me? Cool.
Yep.
So when we're talking about PV equals nRT, right? That's a gas law, right? That's not going to give me information directly about zinc, right? You guys agree?
Yeah.
So what is it going to give me information about directly in this chemical reaction?
It'll give you the moles of hydrogen gas.
Exactly. So we can get to N hydrogen by using PV equals nRT. So if we rearrange this equation, we'll find the partial pressure of hydrogen times the volume of hydrogen divided by RT is what we'll be looking for. So we have T. We have V. Right? But we don't have this guy. What pressures do we have?
Ambient pressure and pressure of water.
Right, so we have the partial pressure of water. And what is the ambient pressure code for?
Total.
The total pressure, right? So we know P tot is this guy. So what would Dalton's law of partial pressures look like for this problem?
783.28 minus 25.509.
Let's write it in variables first.
Okay.
Just so we don't F things up. So it's going to be the partial pressure of water plus the partial pressure of hydrogen, right? So when we solve for the partial pressure of hydrogen, we get exactly what Kevin just said, which is P tot minus pH2O.
When we're converting to Kelvin, do you want us to do 273.15 or just 273?
1.5, please. Sorry guys, I'm trying to make this a little bit more seamless so I don't have to change pages again. It's not great, but we'll deal with it. Okay, so what do we get for the partial pressure of hydrogen gas?
757.771.
You guys all right with that?
I forgot the value of R.
We're going to go through it, but we're not quite there yet. So the next thing that we want to do is, now we have all of our variables for our equation, right? But they are not in the units that we want them to be. So technically, you could use any R you want, but I personally find it really cumbersome to look up an R every time I'm trying to do this problem. So I use this R value, and I convert all of my variables into these units. Does that make sense? So, with the pressure of hydrogen gas, how do we get that into atmospheres?
Divided by 760.
So, partial pressure of hydrogen gas will be in atmospheres. Anybody get this one?
0.997 atmospheres.
Let's see, we got 5 digits here, 5 digits here, so we could definitely get one more on here.
1.
Cool. And what's the other one that we need to convert? Temperature. So just a mild reminder, one of the #1 ways that students get gas law problems wrong is by not converting to Kelvin. Now I rounded the 0.15 to 0.2 because whatever I end up with is only going to have 1 digi in the decimal place, right? But the rounding that you do with your K value, or with your conversion factor for Kelvin, is dependent on how many decimal places you have here, right? Does that kind of make sense? I just like to round before. I think it's easier. So what do you guys get for the temperature?
299.4 Kelvin.
Beautiful.
Rounded after.
Perfect. Okay, so now we can plug all that mess into our PV equals nRT. 0.9971 ATMs times 0.745 liters divided by 0.826 liters atmospheres per mole Kelvin times 299.4 Kelvin. Sorry, I'm going to get rid of this other one here.
I got 0.0302.
0.0302.
Yes.
And that's moles of hydrogen gas. Everybody all right with that?
I got a big ass number. I got 2,710.
No, definitely not. My guess is that you don't have parentheses around these two on the bottom, and that what you actually did was multiply these guys together, divide by this guy, and then multiply by this guy.
I put it all together with parentheses around everything.
But if you didn't put parentheses specifically around the denominator when you multiply them, the way your calculator interprets that is this guy times this guy divided by this guy times this guy.
I see.
Yeah. More parentheses is always better in a calculator. Calculators are very dumb. Does it make sense why I think thousands of moles is a crazy number?
Yeah, I mean,
Cool.
it didn't make sense to me.
Okay, cool. Good. I like that. Yeah, having that intuition is good. Harrison, you want to back him up on this one?
I'm doing it again too, but just to
I
make
got
sure.
1.13 times 10 to the negative 2.
All
Are you
right.
asking about the moles of hydrogen there?
Yes, I am.
Yeah, I got the same number.
Okay, cool.
I got that too.
Yeah, I got it again.
Cool. Okay, so now what do we want to do with this guy?
You want to use it to convert to moles of zinc?
Mm-hmm. So I know from the balanced chemical equation, for every 1 mole of H2, I have 1 mole of zinc. Right? And from the periodic table, I know that for every 1 mole of zinc, there are 65.38 grams of zinc.
I got 1.97 grams.
Same thing.
Are we done?
No.
No. All right. We want to know the percentage of zinc in the original compound. In the original sample, we had 3.9874. Is that right? I'll look.
3.9864.
So close. Grams multiplied by 100.
%49.4%.
Boom. How was that, guys?
Long.
That was rough.
It's way more fun when you get to do these problems in the context of a lab. In the abstract, it's less fun, but maybe I.
Is this the problem that would be on like a quiz or a test?
Yeah.
Okay.
Uh-huh.
Kind of similar to like the third or fourth lab that we did. A little bit, or we're finding like the empirical formula of zinc chloride or
kind of, sort of, yeah. So this would be, because you're talking about the mass percent of zinc. Yeah. It's just that instead of the way that we were doing it before, which was by mass, right? In this case, we're not doing the by mass collection. We're doing the gas collection, right?
Right.
So, not to freak you guys out or anything, but this is actually not a super complicated problem as long as you understand the setup. Because there's only one gas, right? Technically two, because we collected the gas over water, but a lot of the times when we're doing gas stoichiometry problems, we're doing multiple gas reactants and multiple gas products, right? So these problems can get a little hairy, right? When you have 4 different gases, or sometimes even 5 or 6. A lot of the applications for this kind of chemistry are atmospheric. So I love those kinds of problems. I can't give you crazy reactions on a test or a quiz because it would be too much, but definitely expect to see at least one all gas reaction with stoichiometry on a quiz or an exam. Does that make sense, guys? Do you know what I mean by all gas reaction?
Yeah, all gases as reactants and products.
Exactly, yeah.
Will there be problems like that to practice on in the lecture packet?
Definitely, yeah. Let me see.
So it won't be like a surprise on the exam.
Yeah, so number 8 on the lecture packet is a brutalizing atmospheric oxidation problem, which I love. It's super interesting, but I just want to front load by saying that this is much longer than any problem I could ever give you on a quiz or an exam. But it's good practice for going through the steps. When you guys look at the answer key for that problem, it's about 2 pages long. So just throwing it out there. It's a hard problem, mostly because it's just very long. But I would never give you something of that length on an exam.
So for number 6 that we just did together,
Yes.
I didn't think that it was like super hard, but would you agree that like just having like a lot of organization of like
Yes.
what your pressures and like what's what like would
Yes.
help?
Yes, absolutely. I think that the number one thing going into any of the problems with gases and solutions is organization and visually organizing, right? So not just having them written down, but having them written down all in the same place in a systematic way, right? Especially when you talk about having multiple gases in a gas reaction, then things get really complicated really fast, right? So organization is key. Yeah, absolutely, Harrison. Really great point. Any other questions about these? So these kinds of gas reactions are going to come up again in Chem 201 when you guys start looking at reaction equilibrium. So just be aware that while some of the stoichiometry problems that we're doing here are, or in the homework rather, are a little bit painfully long, they're really worth doing because you're gonna see this material again, right? So, homework's not assigned for credit, but I really think, I promise I wouldn't give you these problems if I didn't think that it was imperative that you guys understand this going into the next semester, right? Any other questions about that?